like last Thursday. It was a really long time away. We were going over all the major parts of the heart, and yes, my clicker I think is just dead, not battery dead. It's gross, so I got to keep going over there. But we got over the different, the major parts of the heart. We've got the right and left atrium. Again, it's the person's right side. The right and left ventricle. We went through the valves. The valves are there to ensure a one-way direction of flow of blood through the heart, so that blood doesn't go backward. So blood from the right atria is going to go through the right atrioventricular valve into the right ventricle. We've got a valve on the other side called the left AV valve, also known as the bicuspid, also known as the mitral, that allows blood to go from atria to ventricle and not backwards. You have two semilunar valves that allow blood to flow out of the right ventricle or out of the left ventricle and blood not to flow backwards. There are semilunar, we call them pulmonary semilunar, or the aortic semilunar. Sometimes they just take the semilunar word off of it. If any of those become damaged, blood can flow backwards, which means we're not getting blood to the lungs to pick up oxygen, and we're not getting oxygenated blood throughout the different areas of the body that require it. Maybe it's the computer too. There we go. And I'm like, this was the whole pathway of blood through the heart. Now, this is written out, and I'm one of those, I like a visual heart. It starts at the right atrium. It goes through the tricuspid valve. So you're in the right atrium, goes through the right tricuspid valve, or right AV valve, into the right ventricle. From there, from the right ventricle, it leads through the pulmonary semilunar valve into the pulmonary trunk / pulmonary, pulmonary trunk or pulmonary arteries. They're going to go out to the lungs to go pick up oxygen. They're going to come back to the heart with all of their oxygenated blood. They're going to go into the left atrium, and then we start the systemic. You now have oxygenated blood in the left atrium, going to go into the left ventricle, passing through that left AV valve, also called bicuspid, also called mitral. From the left ventricle, it's going to leave the left ventricle. It's going to go into the aorta, but it first has to pass through the aortic semilunar valve. And that is oxygenated blood. I drew it in red. And then it's going to take that oxygenated blood out to everywhere in the body, all the tissues that need oxygen. And then it comes back into the right atrium using the superior vena cava and the inferior vena cava, and starts all over again. I'm like, you have to know a flow of blood through the heart, not just for general. You're going to have to know it for advanced. You have to be able to know where is blood going from point A to point B, what valve is in between it. And I'm like, the fact that the valves prevent the backflow of blood. And I'm like, so they don't go backwards. It's always a one direction flow of blood. Now again, that's the wordy way of written it. Here's kind of the more, so they're dumping into the right atrium, going into the right ventricle through the valve first, and then eventually from the right ventricle, they're going to pump and go, and I'm like, and split to the lungs to go pick up oxygen. Then the oxygenated blood comes back to the heart, into the left atria, from the left atrium into the left ventricle, passing through the mitral valve, and then from the left ventricle, it's going to go through the semilunar valve, out to the aorta, and bring blood to the whole body, oxygenated blood, and then start all over again. I like it. 2 different ways. You have to know flow of blood through the heart. Now, although you've got one side of the heart is pumping blood to the lungs to go get oxygen, and you've got the other side of the heart is pumping blood to the whole body to deliver that oxygenated blood and pick up carbon dioxide, there are equal volumes of blood pumped to either side. One doesn't have to go as far, and I'm like, the blood doesn't have to go as far because are the lungs close to the heart? Yes. And I'm like, so the right side of the heart, and I'm like, has low oxygenated blood. It's the side that has to pump that blood to the lungs to go get oxygen. So it doesn't have to pump it as far. It's right next door. The left ventricle has to pump blood throughout the entire body. Down to, your toes and your fingers. That's really far. And so the left ventricle wall will show that. The left ventricle wall is a lot thicker than the right ventricle wall. Although there's equal volumes of blood that's pumped through it, that left ventricle has to pump that blood a whole lot harder and generate a whole lot more pressure because it has to pump blood through the whole entire body versus just, right to the lungs and then back. And I'm like, you'll see that because next week we dissect a heart, and you'll easily be able to visually see that huge difference in the left ventricle wall being a whole lot thicker than the right ventricle wall. Now, the coronary circulation is the fact that the heart itself, so we're pumping blood to everywhere in our entire body, but the heart itself also needs some blood. So we have to pump blood to the heart. There's blood flowing through the heart, but that blood itself is not oxygenating the heart tissue. And I'm like, the heart is a pump and it's pushing that blood. And so we have our own circulation. It's called the coronary circulation that's bringing oxygenated blood to that heart tissue itself. Now, I was going to say, yes, the blood supply to the heart, and I'm like, a lot of the oxygenated blood is in the left ventricle. It's where we've got most blood supply because we have to pump it everywhere. But we also are going to have some of that blood coming from the aorta. Got it somewhere. It's going to come from the aorta, and it's going to branch and bring oxygenated blood to the heart tissue. I've got a picture. This aorta is a huge blood vessel, and it's got lots of oxygenated blood from the left ventricle. Well, there are some blood vessels that are going to come off. These are my blood vessels. Again, I'm not artistic. There are some blood vessels that are going to come off the aorta and bring oxygenated blood to the actual heart tissue itself. Now, in the heart blood vessels that are coming off of there that are bringing oxygenated blood, there are lots of junctions. It's not just, okay, there's one blood vessel and that's it. There are lots of branches that come off all of those blood vessels. So that if you get a blockage in one blood vessel here, well, we can still move blood another place. It decreases the chance of damage to the heart if you have a blockage. This is showing some of these blood vessels that are coming off. They're coming off the aorta, that big huge blood vessel near the bottom. We have big huge arteries, one that's feeding oxygenated blood to the left side of the heart, one that's feeding oxygenated blood to the right side of the heart, and they have lots and lots of branches. So that, yes, if something happens somewhere, a blockage is in somewhere, hopefully we can still get blood around it to give blood to the majority of the heart. Now, just like there are arteries that bring oxygenated blood to the heart, there are also veins that are taking the low oxygen, high carbon dioxide blood back to the heart to eventually get pumped back into the lungs to go pick up oxygen. So all the blue are the low oxygenated blood vessels. So circulating around very close to where the arteries are, you have veins that are picking up that low oxygenated blood. They will dump into the right atrium because the right side of the heart is low oxygen. And so you'll have a superior vena cava, I don't know, I could draw another blood vessel, that's bringing blood from the top part of the body, and you have an inferior vena cava that's bringing blood from the lower part of the body. But you're also going to have another couple blood vessels in there as well that are dumping unoxygenated blood from the heart tissue itself. Yep, at least recognize them. Now, if you do have a blockage in the heart, it's called a myocardial infarction. It's not an infraction, it's an infarction, although they look alike. It's the official name for heart attack, is that you've got a blockage or some type of damage to those blood vessels. Blood flow can't get through those arteries that feed to the heart tissue itself. And if you can't get oxygenated blood to the heart tissue dies. Now, the hope is that, yes, there's enough branches we can, work our way around it, and it's how a lot of people can survive for a long time without even realizing there's a blockage. But if you damage heart tissue, wherever that blockage is, anywhere after that that's not getting that oxygenated blood, that muscle tissue dies. And unfortunately, it's a permanent death. That muscle tissue will form scar tissue. Now, worst place you can have damage on the outside of the heart, I wouldn't even say this side, it'd be more like right over here, the left side. If you damage that left ventricle area, it's that left ventricle that has to pump that oxygen. It's so sick, and you have to pump that oxygenated blood through the entire heart. And I'm like, if you have serious damage on the left side of the heart, it's almost always fatal. Now, heart attacks. People survive heart attacks all the time. The problem is, whatever damage has been done, damage has been done. You don't fix it. People will always have a weaker heart afterwards. You damage tissue when that tissue did not have oxygen. There's permanent damage there. So people that survive heart attacks will always have a weaker heart. And I'm like, now, the sooner you realize you're having a heart attack, you can get in there and try to fix that, because sometimes you don't even realize it, until serious damage has been done. Other people start to know signs and symptoms that they're not getting that oxygen to the heart tissue, and the oxygen is not getting pumped to different parts of the body. Can recognize that sooner. Well, if you can recognize it sooner, you can prevent some of that permanent damage, and your heart is better off for it. But it's a permanent damage to the heart muscle. Mm-hmm. No, not recently, but maybe. No, sorry. Found it cool. I liked it. Now, the actual tissue itself, when we look at it, because again, there's skeletal tissue, there's smooth, or skeletal muscle tissue, there's smooth muscle tissue, and there's cardiac muscle tissue. So 3 types of muscle tissue. We're on the cardiac muscle tissue. We've already looked at skeletal. And on my cardiac muscle tissue itself is striated. It's striped. It has myosin, it has actin, just like skeletal muscle does. So it appears striped underneath a microscope. The cells are shorter. Your skeletal muscle cells can run the entire length of a muscle. Maybe not that long, but the entire length of a muscle. And I'm like, these are a whole lot shorter than that. These cells branch. So this is showing that I'm like, it stops there, and another one. Well, this one's got a little branch off and goes to this part of the cell. And I'm like, these cells will branch to connect to each other. They usually have 1, but sometimes 2 nuclei per cell. And I'm like, those are the dark staining purples on there. They do have lots and lots of mitochondria. What do the mitochondria do? They produce energy. They make that ATP. Now, on the picture, all inside, they have sliced open the cell. And I'm like, this is just showing that a lot of the actual cell itself it has not just 1 or 2 mitochondria. It's jam-packed full of mitochondria. This heart tissue could not go devoid of ATP. Needs ATP. There's lots of capillaries, lots of blood vessels. The T-tubules, and I'm like, because we'll talk about T-tubules again, review. And I'm like, are usually a little bit wider. The sarcoplasmic reticulum, the SR on there, and I'm like, isn't quite as organized as skeletal muscle is. Do you guys remember from skeletal muscle, what does the sarcoplasmic reticulum do? Store something. Calcium. And I'm like, because calcium's going to come up today. A lot of the way your skeletal muscle contracts is very similar to cardiac, with the differences that we'll talk about. But they have lots and lots of large mitochondria in there as well. So a lot of similarities to skeletal muscle visually, but there's differences in there too. Also, it's not, and I'm like, only because it's that troponin that's anchored in place that's preventing the heart muscle from contracting. So if we're looking at the troponin levels, they're usually looking at how much is active and how much isn't. If it's low, it means the heart's not going to be able to contract well in those areas. And I'm like, but same, I was going to say, same basic idea with the myosin and the actin in there. We need calcium to bind to troponin, to move it through tropomyosin, to expose all those active sites. Now, the cells themselves, so you can see some of the branching happening, but where the 2 cells meet, anywhere we have 2 cells meet, it's called intercalated discs. It's an anchor. The cells in your heart are attached to each other. They are bound to each other. Underneath the microscope, that stains darker where those cells bind, but it's at those attachments where the 2 cells bind. They are held together by what are known as desmosomes. They make it so the cells don't separate from each other. They're in a permanent bind when it contracts, but also at these junctions, they have what are known as gap junctions. It pretty much means there's still a hole. So although they are stuck together, 2 cells stuck together, stuff can still get from one cell to the other. You still have these little gap junctions, these little tiny holes or pores or channels, whatever you want to call them. And I'm like, at those sites so that ions like sodium and potassium and calcium ions can still move from one cell to another So when one cell has an action potential happening, the cell right next to it also does, because the ions are all moving together. And it can do that through those gap junctions. So it allows the heart to behave as one single coordinated unit because those ions can move through there. Now, I was going to say, energy requirement. No, I was going to say energy requirement, just that it needs lots of energy, and it can get it from different places. And I'm like, but it needs constant supply of oxygen and ATP. All right, pink, orange, yellow, and green, because I might as well get them out, because my hope is that, yes, we'll get through this whole PowerPoint, and there's more questions at the end as well. Some of this is from last time, because I didn't know how far we get through last time. What is the double-walled sac that covers the heart? What is the name of the double-walled sac that covers the heart? And yes, they all have cardium in there. Just, you got to look at the prefix. And covering is a clue. Now, the double-walled sac that covers the heart, it's the pericardium. Wasn't even that, sorry. It wasn't like, peri means it goes around. This is the covering that goes around the outside of the heart. The epicardium is the layer that's attached directly on the heart. Of the following layers of the heart, which one do you think consumes the most energy? Pink, orange, yellow, or green? It is the orange. Why? It's a muscle. It consumes energy. It needs energy for it to contract. Which of the following structures is an exception in the general principle surrounding blood vessel oxygenation levels? Well, let's see if you guess. And then I'm going to explain it. And of course, I can't click. Should have changed my A and C to pink and yellow. Figure it out. It is the green. Now, it's because the general rules, arteries carry blood away from the heart, and veins bring blood to the heart. That's the general rule with arteries and veins. An exception, and I'm like, oh, I should say it, like flip it around. And I'm like, no, that's right. Bring it. Yep. And I'm like, oh, I shouldn't even say that. It is the rules. Arteries bring blood away from the heart. Veins bring blood to the heart. That's the general rule. Now, arteries almost always carry oxygenated blood. Veins almost always carry unoxygenated blood. This is why when you're looking under your skin and you see dark blood vessels, oh, those arteries, are they veins? Those are veins. And I'm like, the veins, although they're not blue, that is a dark, dark red in there, carry low oxygenated blood. The difference, though, the pulmonary trunk or pulmonary artery, although it does flow away from the heart, it's carrying blue. This particular artery is the one artery that carries unoxygenated blood. Because the pulmonary trunk or pulmonary artery is going where? It's going to the lungs. Do we want to carry oxygenated blood to the lungs? No, we want to carry unoxygenated blood to the lungs to go pick up oxygen. And then that oxygenated blood is going to go back into the left atria. I drew this last time, probably a better picture. And I'm like, through the pulmonary veins. And again, veins are going to carry blood to the heart, and veins usually carry low oxygenated blood. But these pulmonary veins just got back from the lungs, so they have lots of oxygen. Yep, yep. And I'm like, so 2 would be going in and dumping right there. Yep. So 2 pulmonary arteries, but 4 pulmonary veins. And so normally arteries carry oxygenated blood, normally veins carry unoxygenated, except the pulmonary. You know, every time you create a rule, you have to have an exception. The presence of intercalated discs between adjacent cardiac muscle cells cause the heart to behave as a what? Hold on a second. What's one of the last things we went over? A single unit. I'm going to come back to this one, because this one we actually go over coming up. So I'm like, I'll tell you the answer. The cells, and I'm like, so cardiac muscle cells have several similarities to muscle cells, which is not a similarity. And I'm like, it's pink, because we kind of lead into it. I'm like, I looked at that before I came. I'm like, oh shoot, this should really be after our next unit. All cardiac muscle cells are not controlled by nerve endings. All of your skeletal muscle cells are controlled by nerve endings, but cardiac muscle cells are not all controlled by nerve endings. Now, cardiac muscle contraction, we're going to get into contracting just like skeletal muscle. Some differences from skeletal muscle. We're going to look at differences and similarities and how they contract. About 1% of the cells in your heart have something known as autorhythmicity. I think it's a horrible word. Or automaticity. Either way, they can control automatically without any neurological stimulus telling it to contract. And I'm like, it happens. You can remove a heart from a body and put it in a dish, and what's it going to do? It's going to contract. There's no brain tissue telling it to contract. It's because some of the cells that are in there have this, autorhythmicity in them. Now, that doesn't last forever. And I'm like, but they can contract without nervous system stimulation telling them to contract. Now, all of your cardiomyocytes, aka the heart muscle cells, will contract, or none of them will. You're either going to create an action potential, and all of the cells are going to have that action potential, and they're all going to contract, or none of them will. You won't have hit threshold. And they also have longer absolute refractory periods. This is a longer time for them to reset themselves where you can't have another muscle contraction. We need that long refractory period so that you don't have tectonic contractions. Because if you have a tectonic contraction, that means it's a contraction that doesn't relax. What happens if your heart muscle contracts and doesn't relax? It just stays in a contracted state. What will happen to you? You'll die. Why? You're not pumping blood anymore. It just stays in a permanent contraction. You're not filling, you're not pumping. And so that having that longer refractory period that allows it to reset itself prevents that possibility of having another contraction and another contraction to form a permanent muscle contraction. Now, some similarities that your cardiac cells have with skeletal muscle when we talk about contraction. Well, we still have depolarization happening. So if you're like, oh, I thought we were done with depolarization. Nope. Depolarization, it's still going to open sodium channels. So back to my little, club axon back in the day when we drew it. I don't know what that was, a couple weeks ago already. And I'm like, you're still going to open some sodium channels. They're going to open more sodium channels. They're going to hit threshold. And you're eventually going to have that membrane potential go all the way from -90 all the way up to +30. And I'm like, you're still going to have that huge influx of sodium going in to cause that depolarization. And then they're going to close. You're going to have the depolarization travel down T-tubules, just like in skeletal muscle. The sarcoplasmic reticulum will release some of the calcium that it's stored. And then that calcium is going to bind your troponin, move the tropomyosin from the active sites, and myosin heads are going to bind to the actin and do their power strokes, and muscles will shorten and contract. Should sound familiar, right? So we just nod. And I'm like, oh, that sounds familiar. And I'm like, because it is. Those are the same basic steps as skeletal muscle contracting. And I'm like, same basic steps as cardiac muscle contracting. But there's more differences, though, than there are similarities. So some good basic steps with some modifications. And I'm like, one, that depolarization that opens the sodium channels, that opens more sodium channels, will also open additional calcium channels. And so, yes, the sarcoplasmic reticulum will release calcium, but that initial depolarization also opens calcium channels, so more calcium rushes in. So if I drew my big club axon, which I'm not going to, sodium goes into the club, but calcium goes in too. And having additional positive ions going in, not just sodium, but also the calcium, gives a longer depolarization phase. And I'm like, now it might cause a plateau. I'm not going to go to the picture yet. It caused a little plateau instead of just, okay, we're going to depolarize, we're going to repolarize. You have your hyperpolarization doing this and a little hyperpolarization and back to normal. You know, there's your threshold. Well, we want a longer depolarization. So once it gets up to the top, this is probably on your next slide. Once it gets up to the top, it stays up there for a longer period of time before coming back down. And it's because you have extra calcium that went in, extra positively charged calcium that keeps it up there higher. So your action potential, the contraction phase, is all going to last longer. We need a longer contraction. We have to ensure that when that muscle contracts, it contracts long enough so we can either push blood from the atria to the ventricle, or more importantly, from the ventricle out of the heart, either to the lungs or to the body. So you need those longer contractions to ensure that blood has enough time to get pumped out. Now, if you open additional calcium channels, when you repolarize, you have to then close those additional calcium channels to reset everything. And then we have to pump all that extra calcium back into the sarcoplasmic reticulum. So kind of, a little modification is you're still going to have depolarization. You're still going to have repolarization. Except now you have calcium going into the club too, not just sodium. Normal that we've talked about, it was that purple. You've got just, depolarization, and your repolarization. However, muscles, depolarization happens very quickly because of all of that extra calcium. All that extra calcium, you have that kind of plateau at the top, so that you've got that longer contraction phase in the heart before everything resets itself. Now, some energy requirements. It has a lot of mitochondria. It had lots and lots of mitochondria. 20 to 25% volume of the heart can be made up of mitochondria in the cells. And so it requires, lots and lots of aerobic respiration to turn out lots and lots of ATP. The heart cannot contract anaerobically. Your skeletal muscles can contract anaerobically. And how do you know your skeletal muscles have gone into anaerobic contraction? You get sore the next day. Your cardiac muscle can't do that. You can't overwork your heart and, wow, my heart feels a little sore. That would be scary. And I'm like, but it's not because it went into an anaerobic state. It has lots and lots of mitochondria. It works best in an aerobic environment. And so it can't really do anything anaerobically. It does depend on a lot of fuel. And I'm like, so it needs oxygen, but it also needs fuel. It needs sugars. It can even use some of that lactic acid. That lactic acid came from sugar. And I'm like, you broke down sugar, and eventually you didn't have any oxygen to do anything with the sugar, and it made lactic acid. There's still energy in it. Our cardiac muscle can pretty much try to use any energy that's out there, and it will use it for an energy source. And I'm like, because it needs energy to contract. Now, the electrical events that are happening. Yes, all of this happens. We have to have depolarization. We have to have repolarization in the heart. And I'm like, but there are different cells that can do this because they don't need nervous system stimulation. They just do this all by itself. Now, the rhythm is set. And I'm like, by your body, how many times your heart is contracting. That can change. Your autonomic nervous system can change your heart rate. Your autonomic means you can't control it. It's autonomic, sounds like automatic. And my example is if you were running or you were scared or whatever, does your heart rate change? Yes. And so I'm like, we do have a set rhythm on how much we depolarize and repolarize and how many times our heart beats per minute. That can change by your autonomic nervous system. The fact that our heart beats, all is one big unified muscle is because of the gap junctions, the fact that we can have those ions moving from one cell to the other, so everyone's receiving the same ions. But it's also because we have these, what are known as non-contractile autorhythmic cells. These are the cells that can cause contractions without needing nervous system stimulation. So they can initiate and distribute electrical impulses throughout the heart without needing any type of nervous system stimulation. Now, how they can do that, and how the fact that our heart is always beating and you don't even have to think about it, is because these cells in there that can generate electrical impulses have what's known, I'm going to say it up there, an unstable resting membrane potential. Your normal cells have a pretty stable resting membrane potential. You have to have some sodium that sneak in to hit threshold to open it. Well, the cells in our heart don't ever flatline. They don't ever have a stable resting membrane potential. There's always sodium sneaking back in. As soon as repolarization is done, sodium is sneaking back in. There's never a flat line where you don't have sodium sneak in. And so I'm like, it always is probably my next slide. And I'm like, always is sneaking in. There's no flat line anymore. And so these cells are unstable. Sodium is always sneaking in. It's always going to hit threshold. It's going to cause depolarization. Your heart will contract. If it was stable and you didn't have sodium sneak in, let's just say sodium would ever sneak in. Let's just say that your heart would ever contract. And I'm like, so the fact that our cells in our heart are unstable, you always have sodium sneaking in, you're always going to hit threshold, you're always going to have a muscle contract, means your heart will keep contracting because of that. So you have this unstable resting membrane potential. Now, kind of some of the same basic steps to create everything. You still have the same basic steps of an action potential. You first have what's known as a pacemaker potential, the fact that you've got that uneven resting membrane potential. It will close potassium channels and it's going to open those sodium channels. So as soon as you kick the calcium or move the calcium back in, you open the sodium and let them back in. And so you always have an ion imbalance. You always have something going in. That's anytime you would have something going out. In depolarization, other than the fact you have sodium going in, you also have calcium going in. It's going to give you the rising phase, and it's fast. You have more positive things going in. And then you're still going to have repolarization. You're still going to have potassium channels open. And I'm like, and all of those K-girls want to leave the club. This is what I'm saying, the pacemaker potential. The fact that there is no flat line. As soon as repolarization happens, sodium starts sneaking back in, allowing you always to hit threshold. And so it's called pacemaker potential. There is no flat line. It's the fact that there always is sodium sneaking in all the time. So we're going to reset everything, but then there's no flat line anymore. Now, in the heart, electricity has to move from the heart through the heart to cause contraction to happen, and it does it in an organized way. In lab, some of this is going to be reviewed in lab next week. As we go through the different parts in the heart where electricity starts and how it travels throughout the heart, it has to do it in a one-way direction because blood has to flow in a one-way direction. And so electricity also has to go in a one-way direction. Now, these are my next slides, but it always starts in what's known as the sinoatrial node. This is where you have those pacemaker potential cells. The ones that are always unstable, those are the ones that are always generating that electrical impulse. From there, it goes to what's known as the atrioventricular node. And yes, we smush the word atria and ventricle together and call it atrioventricular. It's right on the wall between them. That goes into what's known as the atrioventricular bundle. It splits into right and left branches. And then it goes through the outside of the ventricles through what's known as the Purkinje fibers. Your cardiac pacemaker cells generate electrical impulses about every 220 milliseconds. That means you have about 5 of these per second. Now, does that mean your heart is contracting 5 times a second? No, but you are sending electrical impulses like 5 times a second to cause, enough action potential to cause enough depolarization to make your muscles contract. Now, the sinoatrial node, part of its name is the atria. I wish I had more colors. I could use a different color. The top part of the right atria, only the right side, not the left side. The top part of the right atria is where you find the sinoatrial node. And it's really nicknamed the pacemaker of the heart, because it's in the top part of the right atrial, SA node, is where you have that big concentration of electrically unstable cells that are going to generate your electricity through the heart. Now, it's going to generate impulses, and I'm like, that when they hit their threshold, will generate impulses at around 75 times per minute. And I'm like, that's a large enough electrical impulse to cause a contraction. It's not unheard of that your heart will beat 75 times per minute, known as your sinus rhythm. Again, that can change per individuals and lots of different reasons. But from the sinoatrial node, where you have that high concentrations of cells that generate the electrical impulse, that electrical impulse will spread across the atria. It will go all the way over to the left atria. So here's your little sinoatrial node right there. It will spread that electrical impulse to the left atria. It will spread it through the whole right atria, and it will go to the bottom of the atria. There is a wall. I shouldn't say super bottom because there's a valve there, but there is a wall between the atria and the ventricle. And so we call it the atrioventricular node. That electrical impulse is going to go from there to there, to the atrioventricular node. So it's located in the wall between the atria and the ventricle, hence atrioventricular septum is the wall, and it delays the electrical impulse for a split second. So it just kind of holds it. That ensures that the atria will have time to do a contraction before the ventricle gets stimulated to contract. You want the blood to go from the atria into the ventricle before you start pumping it out. So there's a slight delay. Then from the atrioventricular node, it's going to travel through the wall between it's going to travel through the wall between the ventricles. It's called the interventricular septum. The word means a wall between the ventricles. Inter means between, ventricles, in between the ventricles there's a wall. And so it's the atrioventricular bundle. I don't know why they call it a bundle. Just a big bundle right there. So I'm like, it's going to travel through there. Oh, there's my wall right there. And you have your atrioventricular bundle. Now, this right here is the only electrical connection from the atria to the ventricles. It's only through there. The electrical impulses that are generated up in the atria from the SA node don't go to the ventricles any other way. They have to go to the atrioventricular node, then they have to go through the AV bundle, or the bundle, sometimes called the bundle of his. That's the only way they can send electrical impulses to the ventricles. They have to travel through the AV bundle. From there, it splits into two, and we call it bundle branches. It branched into two. And its job is to carry electrical impulses all the way to the apex or the tip of the heart. And the tip of the heart is at the bottom. Normally the tip of things are at the top, but in the heart is flipped over, and it sends electrical impulses to the bottom. So we're sending electrical impulses all the way to the bottom of the heart. It splits into two. And then you have what are known as the Purkinje fibers, or your subendochondrial conducting network. Purkinje, a fun word to say. And and it's those Purkinje fibers. They branch, but these are the fibers that are going to go up the sides of the walls of the ventricle. And they're what's going to cause the ventricle to contract. So your atria will contract first. It becomes delayed for a split second so that the atria can do a full contraction. Because wherever I have electrical impulse, I'll have a contraction. And then the ventricles will receive that information, and the ventricles will contract. So we're going to move blood from the atria to the ventricles and then out of the heart. And it's this electricity traveling through the heart that allows the atria to contract first, then the ventricles. Bigger picture of it. You have your SA node where you have all those cells up there that are unstable, that are generating that heartbeat or rhythm, sends information to the AV node. It goes down towards the ventricles, the atrioventricular bundle. It branches, so you get your bundle branches, and then it travels up the ventricles so that the ventricles will both then contract. So first you have to have that electricity, then you have to have the heart that's able to contract. Now, things that can happen. You've got electricity that can happen. Things can happen so that our heart doesn't contract like normal. One, we can have what's known as an arrhythmia. Now, anytime you put A in the front of anything, it means what? Without. So this means without a rhythm. We have to have a rhythm with our heart. Our atria have to first receive electrical impulses and contract, then the ventricles below it have to receive electrical impulses and contract. We have to contract atria, then ventricle, then atria, the ventricle, and so on. And for us to have a one-way direction of flow. If something messes with that, it's called an arrhythmia. You have some type of uncoordinated electrical impulse, and you're not going to send blood from atria to ventricle and out. And you don't have the correct rhythm anymore. We can also have something known as a fibrillation. It's a rapid irregular contraction. This is a normal heartbeat contraction. And that is normal heartbeat contraction. This is an atrial fibrillation. There's no coordinated. There's just electrical impulses that are shooting out all over the heart, which means you're not going to have a nice coordinated atria contract to send blood down here and ventricles contract to send blood out. You just have your heart is having electrical impulse all over. And if it has an electrical impulse all over, is it going to be able to send blood out in a nice one-way direction flow? Like, let's send blood to the lungs. Let's send blood to the heart. Let's send more blood to the lungs, more blood to the heart. It won't. It's a completely useless heart contraction. There's no rhythm to it. You're not going to send blood to the lungs to get oxygen and then send it to the body to deliver the oxygen. And your blood circulation will stop. There's no rhythm anymore to have one part of the heart contract and then the other. This can lead to brain death if you don't get oxygenated blood to different parts of your body. Now, when you have fibrillation, you treat it with a defibrillator. What do they do for a defibrillator? They shock you. You can get those little portable defibrillators now, and they, shock you. They're literally shocking. There's always two bands. The idea is that you have, or two little patches, one at the top and one at the bottom. The idea with that shock is it wants to have an electrical current go straight across. It wants that electrical current to start here and go straight across. The hope is that's going to shock that SA node back into rhythm. And so when it shocks in this direction, it's hoping that it will shock the SA node and that electrical impulse will start to regenerate on its own again. And it's just something has happened to cause the SA node to be completely out of rhythm. That shocking can most often, if it's in a true fibrillation, shock it back into a rhythm again. Another thing that can happen, another imbalance, is you can have a heart block that's defective. The AV node, my little AV node right there, has to receive information from that sinoatrial node and then send it down into the ventricles. Well, if the AV node or even that AV bundle isn't receiving the electrical impulse, the atria will contract, but the ventricles won't. Or the ventricles won't contract enough. It's like, well, I only get small little bits of electrical information, and so the ventricles aren't going to contract as often as they need to. It's called a heart block. It's not that you have something in the heart blocking the flow of blood. It means there is a blockage in the electrical impulse. Can't go from the atria to the ventricles, which means the ventricles aren't going to contract. They're not going to pump that blood out to the body or out to the lungs to go get oxygen or deliver oxygen. It's treatable if you know what's going on. And they can put an artificial pacemaker in, and that pacemaker receives the rhythm from the sinoatrial node and will trigger the ventricle to contract. And so it's its own little pacemaker, it's its own little receiving device. Cool thing about pacemakers, and they've gotten really high tech. And although they will sit right underneath the skin, and there's electrodes that go to a heart they look cool. And I'm like, those pacemakers, although they sit underneath the skin, they can send emails. They can send text messages. And I'm like, they can actually send emails and text messages right to your doctor. And I'm like, whether you knew it, your body was sending emails and text messages to your doctor to say, like, yeah, I'm still on rhythm. It's still working correctly, even though it's underneath your skin. Now, measuring all this electricity in the heart. We know depolarization happens and repolarization happens. And as soon as you have those electrical impulses, you know contractions are going to happen. Well, we measure it all using an electrocardiogram, known as an ECG. But we also call it an EKG. I'm not sure why K and not C. To me, it would be an ECG for electrocardiogram, but we like to call it an EKG. And it's looking for all the action potentials. It's looking for all that imbalance in action potentials. It's looking for the depolarization and the repolarization. Now, there are, get rid of this, 3 waves on your electrocardiogram. Has anyone had to have an electrocardiogram done? Is it just you? They're interesting. They go pretty fast, but there's tons and tons of electrodes. There's a P wave. Ooh, let's see if I can draw this accurately. No, that's not accurate. Doesn't go down that far. There we go. It's probably not, it's not drawn to scale. And I'm like, but there's first a P wave. This is a depolarization of the sinoatrial node. So this is depolarization happening in the atria, which means the atria are going to contract. So your P wave is your atria depolarizing. They're creating an action potential. Your atria are going to relax. The QRS complex is this whole little section here. And this is where your ventricles are going to depolarize. Which will cause your ventricles to contract. And we want atria to contract and then ventricles to contract. And the last one, your T wave, I could have labeled this. The T wave is where your ventricles repolarize. They're resetting themselves. Now, depolarization is going to be the contraction, and repolarization is going to be the relaxing part. Electrically, it's resetting itself. Now, the QRS, this main spike, is because the ventricles are depolarizing. Atrial repolarization resetting is happening in here, but this bar gets even smaller. It's, you know, if we had to draw it, it all happens at the same time, but it would probably be like that equivalent. It doesn't do a lot electrically. Most of that QRS is the ventricles depolarizing. Oh my, there's my better picture. There's your atria depolarizing. There's your QRS complex. That's where your ventricles are depolarizing. And your atria are repolarizing. And then the T wave is your ventricular repolarization. Ventricles are repolarizing or resetting themselves. Now, this is just showing them, like, again, anything in yellow is depolarization. Your atria are going to depolarize first. It starts at the SA node. Your atria are going to depolarize. That electrical impulse will go down to the ventricles, so the ventricles can depolarize, the yellow. And when the ventricles are depolarizing, what are the atria doing? They're resting. They're repolarizing and resetting themselves, so that you always have atria depolarize, then ventricles depolarize, atria contract, then ventricles contract, and I'm like, so that you still have this one-way direction of blood. Now, again, we can see a lot of abnormalities when you do an ECG or an EKG. Your normal rhythm, you should be able to see that big QRS complex, and I'm like, a P wave before it and a T wave after. And I'm like, however, there are times that you could be, and I'm like, missing some of your QRS waves, and I'm like, and you have lots of extra P waves. That's usually a heart block. And I'm like, is that your P waves, you're still going to have atria contracting, but your ventricles aren't going to depolarize and contract. And I'm like, because they're not all receiving the information. There's your ventricular fibrillation irregular. You have to take advanced so you get to study these more. I'm not going to go into all the different abnormalities that you can see on an ECG. Now, when you hear your heart beating, it has two sounds. They call it lub and they call it dup. So the next time you put your ear on someone's chest and you hear that thump thump, thump thump, well, that's lub dup. Lub dup is the official sound for it. What you are hearing are the different valves closing. And I'm like, your heart makes no sound when it contracts. It's a quiet heart when it contracts. All you're hearing is the valves closing. So when blood goes from the atria to the ventricles and those valves snap closed, the atrioventricular valves, that's your first lub. And then when heart leaves, God, this is messy. When heart leaves through the ventricles and travels through the semilunar valves, whether it's the pulmonary or the aortic, and I'm like, the heart valves will close after that, that's the dup sound. So when you hear the, thump thump or the lub dup, and I'm like, the first is blood going from atria to ventricle, and the second is blood that, went out of the ventricles, and it can't go backwards because those semilunar valves are closing. Now, the pause means your heart is relaxing. The problem is, I'm like, when they listen to your heart, when you go to the doctor and they put that stethoscope on several different places, they're listening for the closing of all four. They're listening for the right and left atrioventricular valve closing. It should be a nice, quick snap shut. They're also looking for the semilunar valves closing, a nice, quick snap shut. If they don't hear that nice snap shut, they're hearing what's called a heart murmur. Is when it tries to close, it kind of does a little bubble sound as blood flows backwards. And I'm like, that means the valves aren't working correctly, and you don't have a great one-direction flow of blood. Because instead of the blood leaving the ventricles and going out to the body or to the lungs, it might be trying to go backwards. Now, depending on how bad it is, and I'm like, it might not be bad at all. And you're like, well, you've been surviving so far, you're fine. Maybe 30, 40 years as your heart deteriorates anyways, we'll have some valve replacement, but a lot of times people can survive with heart murmurs just fine. I was going to say, those are the four places that they listen on your heart. And I'm like, so they're listening to the four different valves on your heart. Now, as we are circulating blood around the body, and I'm like, there are two phases to circulating blood. As we've already talked, there's contractions and there's relaxing. There's the depolarization, there's the repolarization. And I'm like, anytime your heart contracts to send blood somewhere, it's known as systole, or the contraction phase. And I'm like, the relaxation phase of the heart, when it's filling with blood, is known as the diastole. Now, my morbid way of remembering which one is which is, the diastole is always the relaxation part. Oops, relax. Is that you're never more relaxed than when you die. You're never more relaxed than when you die. And so that's my morbid way of remembering which one is which. So diastole is the relaxing part of the heart, and then I think, all right, well then systole is the other one, where the heart is actually contracting. And so we always have different parts. If the atria are contracting, to send blood from atria to ventricles, the ventricles are relaxing, and they're just filling with blood from the atria. And when the ventricles pump blood out of the heart, well, the atria are relaxing, and they're filling. And I'm like, with blood. So I'm like, they have three steps, but it's all filling and relaxing and then pumping to send it from one spot to the other. So when the ventricles are filling, when your ventricles are filling with blood, your atrioventricular valves are open so that blood goes from atria to ventricles. 80% of all the blood that goes from atria to ventricles does it passively, which means you don't even have to contract and push it. And I'm like, it wants to go there because of blood pressure. And I'm like, when the atria contract, it forces that other 20% from the atria to the ventricle. How much blood you have in there at the end of the atria contracting and your ventricles are full is known as your end diastolic volume. And on average, end diastolic volume is around 100 milliliters between the two ventricles, on average. It varies between different people's different hearts. And then the ventricles are like, all right, we filled. So we now have to start to contract. So when the ventricle's job is to contract, the atria are relaxing. They're starting to fill with more blood. And then the ventricles are starting to generate pressure. They're contracting. And they're starting to squish down on the blood that's in there. Now, right when they start to generate that contraction, it's going to generate enough force that it will snap close those AV valves. The AV valves just don't close by themselves. When the ventricles contract, it closes those AV valves. But it's just a start of contraction. So we've generated enough pressure to close the AV valves, but we haven't generated enough pressure to open the semilunar valves, my little green ones in here. Now, at that point, that little split second in there, when you've closed the AV valves, but you haven't opened the semilunar valves yet, it's known as isovolumetric contraction. What's the iso mean? Like an isosceles triangle? Means the same. Yep. And so I'm like, an isovolumetric contraction means we're in the contraction stage or phase, but the volume isn't changing yet because we're not moving any blood out. All we've done at this point is we have every valve closed. When the ventricles generate enough pressure, it will push those semilunar valves open so that blood can flow out of the heart. Now, after the ventricles contract, not every drop of blood will leave the ventricles. A lot of it does, but then you're going to end up with something known as end systolic volume, which on average, for my easy numbers, is there's still about 25 milliliters of blood left in there. We pump a lot out, 75%-ish, and I'm like, but there's still some volume that hangs out in there. Now, we will eventually start this all over again. And I'm like, but after we've pumped that blood out into the aorta, into the pulmonary arteries to go get blood from the lungs, we've pumped all that blood out. When the blood wants to come back, because it doesn't want to go into those blood vessels, when the blood comes backwards after it's pumped out, that pressure backwards from those blood vessels is what closes the semilunar valves. That's when you hear the dup. And I'm like, it's just the backwards pressure of the blood wanting to flow backwards to the heart. It's like, I don't want to go to the body. I want to go backwards to the heart. And when that blood comes backwards and snaps shut the semilunar valves, we can actually see a quick increase in blood pressure. It's called the dicrotic notch. You'll see it on my next picture. And so at that point, you now have all your valves closed as well. And so it's called the isovolumetric relaxation. Is you're still just filling with blood, but we, close the semilunar valves and we still have the AV valves closed. I just wanted to point out the dicrotic notch, that little green, upwards. This is showing blood pressure. When the ventricles contract is when you have the highest blood pressure. It's a lot of muscle pressure back there. And I'm like, but after that heart contracts, blood, when it flows backwards to snap close the semilunar valves, you'll actually see a quick little jump in blood pressure because it hits those valves and just generates a little bit of pressure. I know I'm not going to finish this today, aren't I? So close. What can I preview? And I'm like, I was like, I don't know how far I'll get, so I'll just tape the whole thing. So I've taped it. You can fast forward to this part. And I'm like, but the last parts of it talks about cardiac output. It's really how much blood your heart can pump every minute. And I'm like, and I talk about some of the things that can affect it. But cardiac output is, what's your heart rate? How many beats per minute does your heart beat times what's known as stroke volume, which is the difference between your end diastolic volume and your end systolic volume. And what's the difference between 125? 75. And so, on average, you take your heart rate and multiply it by 75 milliliters, and on average, you pump a little over 5 liters of blood around your body every single minute. And I'm like, so a lot of the rest of this goes over, well, what are things that can affect stroke volume? And like, what are things that can affect end diastolic volume and systolic volume? Well, I was hoping I'd get through it all. So your job before I see you next time, watch the last little bit of it. What are things that can affect your stroke volume? The blood vessel worksheet is on Thursday. There are questions on your exam on Thursday based on the blood vessel worksheet. So make sure you do it and study it. I think there's 4. I was going to say, I was kind of looking, I was like, 1, it's like blood vessel, but it's also heart blood vessel too, so kind of can go worksheet versus also this stuff. So finish watching this, study, do a worksheet. We are going to start the respiratory system on Thursday. There is an intro video. I know it's lots of videos. The rest of this shouldn't take very long. And I'm like, but the intro video goes over basic parts of the respiratory system so that on Thursday we can talk about how does it work. And I'm like, the intro video, it's like, the nose, and I'm like, the trachea and the branching and all that kind of stuff. What are the major parts? But it's good to watch so you understand the major parts when I start talking about them on Thursday.